Welcome back. We will continue with the applications of network biology. There are many applications of network biology and we've started seeing a few of these applications. Today we are going to focus on applications of community detection in a sense. What are we going to do? We are going to see how we can try and identify disease related modules in biological networks. Very interesting backstory to this. This was a challenge that we participated in a few years ago and so on, and I'll give you further details as we go along. Just a quick recap of networks in biology. There are various types of networks that exist in biology. It could be metabolic networks, protein interaction networks, gene regulatory networks, signaling networks and so on, and including protein structure networks and so forth. There are so many different kinds of networks. You may have seen pictures like this. I have discussed this previously in the course and so on. And if you see, cellular function itself is a result of all these underlying networks. So these networks together are the cause for cellular function and even disease and so on. So disease is basically not the dysfunction of a single gene, but you can really think of it as the dysfunction of a network going wrong, causing various kinds of problems that you see. Community detection graphs is a classic problem in graph theory. We did talk about Zachary's Karate Club. This is the picture that you see on the right. So there were two factions that formed in a karate club, and you see the two different colors. These could be very well predicted by various kinds of community detection algorithms. So there are many algorithms for community detection. We did overview a few. I would like to remind you that we talked about the Girvan Newman algorithm, or there are basic algorithms that are based on clustering and so on. But how do we use, can we use these existing algorithms directly on biological networks, or are there unique challenges in the context of biological networks? I think the answer is obvious. There are many unique challenges when we look at biological networks, and how do we tackle those? Can you readily apply these algorithms? Well, the answer is mostly no. Well, you can, but you still need to process those results in a different fashion and so on to break down the large modules that you get into more smaller and biologically plausible modules and so forth. Recap, what are communities or clusters or modules? These are groups of nodes that are very tightly knit with one another. And what do I mean when I say tightly knit? It means that crudely they have lot more intra-edges, meaning edges between them, than inter-edges, so edges that connect them to the rest of the world, outside communities, outside a small cluster or outside this small community. Okay, and you see a few examples on the screen. So one of them is a citation network in various fields, and you see that papers in statistical physics are more likely to cite papers in statistical physics. Papers in mathematical ecology are more likely to cite papers in mathematical ecology and so on. Right? But occasionally you do have papers from one field that are citing others and things like that. So these would be interdisciplinary papers that cover multiple interesting topics and so on. This is one aspect of networks, just to refresh your memory. And you can also use it to take a complex network and sort of make it into a more tractable network by simply coalescing these communities into nodes and looking at the connections between them and so on. Modules are very important in biological networks. There are many functions in a cell that are carried out in a highly modular fashion. And modules are basically important functional units. They could be groups of physically or functionally linked units or proteins or various kinds of entities, basically nodes in the graph, that work together to achieve a distinct function. And there are many modules that are present in biological networks. It could be either a metabolic network or a protein interaction network. You will see that there are lots of different kinds of modules that are present. And how do they show up? They show up as highly interconnected groups of nodes which are much more densely connected between one another, with one another, than you would expect by chance. We talked about this a few classes ago when we looked at motifs and so on. Basically, we were talking about so what is a motif? A motif is a bunch of nodes, is a subgraph of a network that is far more overrepresented in the real network compared to what you would expect by chance. And for this chance expectation, we decided to create an ensemble of networks that would give you a picture of what would be the expected distribution of these kinds of motifs in similar networks, and by similar we mean nodes with the same number of nodes, same number of edges, therefore density, and also degree distribution. So these were the three things we were talking about: same number of nodes, same number of edges, which automatically means density, and also the degree distribution itself. So if you had a power law network, you would again generate various power law realizations, except that they no longer have functional or logical resemblance to the real world network, meaning a single node is no longer has the same meaning as it had in the real network, because you basically rewired it, right? So you've lost the original meaning, logic of the original network, but still satisfies, is still very similar to the original network in many ways. So this gives you your random ensemble, and now from this you get a distribution. Then you see where does your network occur in this distribution and so on, and you use this to estimate how far, how novel or how different, how surprising, low p-value, how surprising is your network compared to the random networks. Modules again are groups of nodes that are much more densely connected than you would expect in a normal network, in a random network. And modularity is an important design principle both in engineering and in biology. You see it commonly occurring in various spheres. It also enables the interrogation of smaller tractable subsets of large networks, as we were talking about a couple of slides ago, wherein you take a large network and you sort of coalesce these modules and you look at module level properties of the network, because sometimes these networks are so large, so studying nodes individually becomes very, very challenging.